Yesterday we started looking at implementing the equalizers in the receiver. So if it's a linear equalizer, it doesn't matter if it's in the transmitter or the receiver. The only difference will be in the implementation details, because the receive equalizer, the input values are analog, whereas for the transmit equalizer, the input values are digital. So that makes some difference in the implementation. And if we choose to do the equalization using an FIR filter, we have many options. One is to use continuous time FIR using transmission line, or you use a lumped equivalent, that is, I will call it LC transmission line. You mimic the action of a transmission line using L's and C's, and you generate a number of delayed versions of the signal, and you take the weighted summation in order to get the output of the equalizer. Yeah, but you need to, you mean passive RC or active RC? Passive RC, if you use a passive RC filter, what will be the delay of this? Let's say the group delay of this at low frequencies. What is the phase response of this circuit? So let's say delay using RC. What is V0 by Vi? 1 by 1 plus SCR. Okay. And what is the, if you plot the magnitude response, it has a 3 dB roll off at 1 over RC. Okay. And if you plot the phase response on a log scale, this is minus 45 degree line. Okay. And at this at low frequencies, what is the delay? What is the phase response of this? What is the phase response of this filter? Minus tan inverse omega CR. And what is the group delay? Are you familiar with the idea of group delay? So it's basically, it is just minus d phi by d omega, or 1 over 2 pi d phi by df. And what is that? Okay. So approximately the delay is RC at low frequencies. And what is the delay you want if you are transmitting at 1 gigabits per second or a particular symbol rate TS? What do you want the delay to be? TS. Okay. So let's say we make this equal to TS. So what will be this frequency in terms of TS? Remember, this is omega. This is 1 over TS radians per second. So what is the bandwidth of the filter in hertz? So let's take 1 gigahertz. We are talking about 1 gigahertz system. Okay. So this is 1 nanosecond. So what is the bandwidth of the 160 megahertz? So it is 1 over 2 pi times 1 nanosecond equals 159 megahertz. So is there a problem here, or is it okay? The reason for putting the equalizer is that the channel is low pass and we want to emphasize the high frequencies. Now this is not a pure delay, it has some magnitude roll off, and the bandwidth of this circuit is much less than Fs by 2. So you can't really use this as a delay because of its own band limiting. Okay. So besides the fact that the delay is not uniform with frequency and so on. So if you want uniform, if you want to operate like a constant delay, you have to operate in a narrow band around here. Okay. Anyway, if you adjust the low frequency delay of this circuit to be 1 nanosecond, the bandwidth of the circuit will be 159 megahertz, which is not sufficient. Okay, this itself will cause ISI if you pass data through it. Okay. And remember, you don't need just one tap, you need many taps. Okay, so you can't really use it. Is this clear? The question was, why not use RCs to make delays? RCs give you not only delay but also high frequency limiting, and the high frequency limitations are just too much to handle. Okay. So if you, instead of RC, you use LC sections, then basically you can extend the bandwidth of this. Okay. In the limit, when you have infinitely small L's and C's, but infinite number of them, you can make a transmission line which has no attenuation but a uniform delay. Okay. But when you have lumped L's and C's, it will have some bandwidth, but it will be better than the RC case. That's why you can't use passive RC structures for delaying the signal. In other words, if you think about it in the time domain, if you apply a step, what you get out will be what? A rising exponential. And roughly speaking, this is what we call the delay. But you can see that the second waveform doesn't have anywhere near the shape of the first waveform. And the more you try to delay it, the less it looks like a step. Okay. So if you try to increase the delay, normally if you have ideal delays, what you want is, for a particular value of delay, you want something like this. For the higher value of delay, you want this. But in RC, what you get is not those, but For some value you get this, for some other value you get this one. That itself causes intersymbol interference, because the response of this spills over into the next symbol. So that's why you can't use RCs for delay elements to make FIR filters. Is this okay? So you can use transmission line or simulate the transmission line with L's and C's using a lumped approximation, or we can use sample and hold circuits to implement delays, and finally we can also do A to D conversion plus a digital filter implementation. Okay. So all of these will have various trade-offs. The issue with the transmission line is that it occupies a large area even if you approximate it with lumped LC elements, and also they are not really easily tunable. That is, if you want to change the data rate, you can't really change the delays of the transmission lines accordingly. It still gives you a high frequency boost, so over a narrow range you can certainly use it, but you can't tune the circuit over a wide range of frequencies. The sample and hold and the A to D converters don't have that problem, because the delay essentially is determined by the speed of the clock, the frequency of the clock. So they are very much tunable, but then you may have a problem with power dissipation, especially in the A to D conversion case, because you can have a complicated FIR filter working at very high frequencies. So we will look at more details of these, but whichever type we use, we would like to adapt it to the channel. That is, we don't know the channel, we want to adjust the coefficients of the filter dynamically so that it equalizes the channel very well. Okay. And in the receiver you can do that, because the equalizer and the equalized signal are sitting in the same place. Both are available. So you can look at the equalized signal and somehow do something to it, or at least see whether it is ideally equalized or not, and do something to the coefficients so that the output of the equalizer becomes more or less ideal. More or less ideal meaning at the sampling instance there is no ISI. How would we go about doing that? See, the reason we didn't do adaptation when the filter was in the transmitter was, why? Why didn't we do adaptation when the filter was in the transmitter? Yeah, somehow you have to send back the data to the transmitter to adapt the coefficients. It is more difficult. It's certainly possible, but it is more difficult. In this case we can do it more easily. So let's say I have an FIR filter. Okay, so let's say we have binary data. Okay, this is sent across a channel, and I have the receive FIR filter. Okay, so this has a certain number of coefficients. You can assume whatever number you want. You beforehand determine that this many coefficients are sufficient to cover the range of channels that I am likely to encounter. Obviously, you can't make any you can't make an equalizer that will equalize any channel completely arbitrarily, but you can make it, you can choose the approximate number of taps and so on. So, now what do we do? So the receiver will look something like this, and it will be followed by a decision block. Let's say it's a comparator, a binary decision block. What is it that we want to do? Yeah, what you said is right, that you have to somehow know what to expect and then adjust what you receive to what you expect. But what is it that you expect? Okay. Yeah, it can be of lesser amplitude, it can be of higher amplitude also. So what do we do? What is it that we expect? Huh? Yeah, you expect 1 or minus 1, that's correct. So here we'll have 1 or minus 1, but you don't know whether it's the right one or not. Okay, that's an issue. Meaning here you will always, because this is a comparator, you will only get plus or minus 1. Okay, but the thing is, you may have got a minus 1 when it's supposed to be a plus 1. That you can't say. So when it's perfectly equalized, what should happen here? So let me apply the sampling also, sorry. Let me assume that the sampling phase is correct. So if it is perfectly equalized, here also I should get plus and minus 1s. Okay. So what is the measure of error that I can use? Correlation. How do you compute that? Mean square error. So you can just look at the difference between the two. Okay. Let me call this y, and this is y hat. So I take the difference between the two, y minus y hat. If it's perfectly equalized, what should this be? 0. Okay. And if it is not equalized correctly, this will be non-zero. So somehow I have to drive this to 0. Does it sound okay? What you receive at y is correct or not? No, I mean this is a linear system, right? So if you get exactly pluses and, I mean you can think about it, I don't think that what you say can happen, that it will give you plus and minus ones arbitrarily, but which have nothing to do with the plus and minus one that you send at the transmitter. Yeah, whatever it is, at the sampling instant you should only get pluses and plus one and minus one, right? Is that okay? But why will the sign be flipped? Okay, let the sign be flipped, fine. What does it mean? No, if it is flipped, again that's not a problem, right? So for instance, if this filter, when it's ideal, has a transfer function h, and I turn it to minus h, that will still work, okay? So then all bits will be flipped, but that's not really an issue. I mean a bit rate of 1 is the same as bit rate of 0, right? Is that okay or not? Yes or no? So if all bits are inverted, okay, that means that I somehow missed the sign somewhere, so I can always put it back. So that is usually not a problem. Yeah, that we'll see. Yeah. Okay. No. If it is 1, how will it be less than threshold? The threshold is 0, right? Okay. No, why will it? The comparator will give you negative minus 1, but this error will not be 0. No, you should do this. I'm not saying you look at just one particular sample and make it 1, right? You do it so that if it is working correctly, for all times I should get 0 here. Is that okay or no? Is there some other combination which will give me 0 everywhere? No, you are saying, okay, at some particular instant of time, maybe it will give me a 0 because. Okay. Okay. Yeah. Let's say it gives 0.8. Let's say, what is less than the threshold? Less than. Okay. Yeah. No, I didn't say that. But I mean, that should happen for every bit, right? You are just looking at one particular case. What does it mean? Yeah. You are saying that you will invert the sign of the filter, right? Whatever is similar to what he said. It is the same. So what is it? Huh? Yeah, so that is the question, and that's why we use the output of the comparator. And the output of the comparator itself may be in error. That's what you are talking about, right? Okay, let's say magically I had the data that I was sending here, I had it here also. Okay, so obviously if I had it here, there was no need to build the transmitter, but for now let's imagine that we have that. So I can take the difference between these two and I should get 0, right? If it is equalized properly. Is that okay or no? Yeah, that's correct. So sometimes it is correct, sometimes it is not. Yeah, and you have to drive it, but if this error is 0 for all time, then you could not have made an error. I mean, for some instance of time, maybe what you sent was a 1, but here you get something negative, so here you get a minus 1. Okay? But it's not as though for every instant of time, you will get this to be the opposite of this. The only way that will happen is if the sign of the filter is reversed. Okay? That's what I mentioned earlier also. Why? What can be mentioned?
When the worst case will be when means transmitting a sequence of -1 and suddenly it will be 1.
Yeah.
In which case this won't be -1, but it will be at least above -1, so we will detect an equal.
Yeah, that's what. We will detect an inequality, but what he is saying is because you detect a negative value, you will drive that to the negative value. That's not how it works, meaning I try to get a condition where it's not that every bit I want, every bit I drive the filter instantaneously. That's not possible. What happens is, I will drive the filter towards a direction where this error sequence is 0. Yeah. Yeah. Yeah, that's correct. Actually, that is a good point. So, if I send only plus ones, I can't use this technique. But at the same time, I don't need equalization either in that case. So, let's assume like random data. So, all these are like more involved details, because sometimes you have to send a known pattern. Known meaning you don't have to send the pattern in a parallel path like this, but you know what you are sending beforehand. Okay. Or maybe you send known sequences like you send 5 ones, 5 zeros, 5 ones, 5 zeros, and after that you shift to some other sequence. You can do that also. But for now, these are known as training sequences, right? You want to train the equalizer with some sequence so that you get the adaptation correctly, and after that you send the random data. But it is possible to do it even without anything. Okay. It is known as blind equalization, and that is you just send random data and it will somehow go and equalize that. So all I am saying now is, again, there is some mathematics involved here. We'll deal with it in the coming classes. But what I am saying here is that if I somehow adjust this filter so that the error between the comparator's input and output is 0 for all time, I have got perfect equalization. Is that believable or no?
Not sufficient if the output of the channel is only incorrect. After the input to the residual filter,
Yeah.
it's doing the wrong data.
Okay. What is wrong data?
Something was saying and a
No, okay. What I am assuming here is that this is a linear filter, the channel is a filter, and this is another filter.
There is no bit pattern not changing and output of the receiver at all.
Now, what is the bit pattern? It's some analog waveform, right? So it is changing, but it is changing as the result of some linear filtering operation. Huh? Yeah. Oh, yeah. During adaptation, yeah, that's true. I mean, before it is adapting, like while it is adapting, you can have errors.
Even after adapting certain particular sequence, some sequence generated suddenly may go out of adaptation, but it's not reversible.
How? Why?
Because long sequence of ones and just suddenly -1.
No. See, if it is, let's say you take some random bit pattern, right, which has certain combinations of zeros and ones, lots of combinations of zeros and ones. Now, this is a linear filter. So, if it is giving you 0 error for that, now any other bit pattern can be realized as a linear combination of other patterns, right, because of linearity. So, that won't happen. What you describe won't happen. It's not that it will give you 0 errors for certain patterns and then non-zero error for some other patterns. Comparator is not linear, but we are making sure that at this point we are getting plus ones and minus ones at the sampling instant. Okay, still not convincing. So let's take a PRBS pattern which has all possible 7-bit patterns. Let's say it's a PRBS 7, and then after doing adaptation, I have not even said what adaptation is, but after doing it, I will get all zeros. So that means that for any possible 7-bit pattern, the ISI has been cancelled because of the filter. Is that okay? Now, at the very least, if the ISI is less than 7 bits long, for any other possible pattern also it is cancelled out, isn't it? Is that okay or not? So, what I am saying is, let's say you send all possible 7-bit patterns, and somehow you adjust the coefficient so that for this particular thing, which could be coming out of your 7-bit long PRBS generator, the error is 0. Okay. Let me also say that the ISI has less than 7 taps. Okay. Now, whether I use a 7-bit pattern or a longer pattern, I will still get the ISI will still be 0, isn't it? If the number of taps in the channel response, if the total number of taps is less than 7, then by covering all the possible 7-bit patterns, I have covered all possible ISI cases. Is that okay or not? Yeah, it is linear. Yeah, no. Where is the? Oh, you are saying how we will adapt it. Yeah, because it is the coefficients are changing. Maybe during adaptation it is time varying. It is not non-linear. It is time varying.
Can we treat it as linear for a substantial?
Yeah, that is the. Yeah. So basically, let's say we operated with constant coefficients for a certain amount of time. We observe what happens to the error sequence. Then we modify the coefficients. We operated with the new coefficients for a certain amount of time and so on. So at least for that amount of time, it is linear. So what is the verdict? Still all hokey. So it does work. I mean, I'll justify it more as we go along. But a measure of error is something like this. You compare what you receive to what you expect, and in this particular case, what you expect is the output of the decision. At least you know that if everything is operating correctly, then there is if you look at the difference between the input of the decision block and the output of the decision block, it will be 0 at the sampling instance. Okay? Maybe I have not proved that it is sufficient to do that, but if everything is working correctly, the error between here and here is 0. Okay, so I do detect the error between these two. Then what can I possibly do? How do I change the coefficients of the filter now? At least, even if you are not 100% convinced, take it now that if I get to a condition where the error between the input and output of the decision block is 0, the channel is perfectly equalized. Okay, take that for granted, but now let's see how to go about making that. Okay, so we measure the error between the input and output, the error between this and this, and it is not 0. So what can we do?
Suppose that y will get plus 1.
Yeah.
So by pass, that data will pass to that comparator.
Yeah.
So there will be a delay.
Let's assume there is no delay here. Yeah. It's a sample data stuff, right? So you are operating only on the samples. So the delay through this doesn't matter. Because I just want the difference between this number and this number. I have one clock period to process that. Like every digital circuit has a delay, but that doesn't mean if you make an adder, the output result will be wrong. It will just come after some delay. So basically the adaptation is changing the coefficients of the FR filter. But how do you do that? No, not how to implement the changing coefficients. But how do we change it? I have, let's say, coefficients of 1/2 and 0.25, and I see some error here. Like what do? You do increase this, decrease this, maybe 1 minus half plus 0.25. I am not talking about how to implement a variable coefficient, right? Yeah, whatever, okay, like forget the implementation. Like I have 1 minus 5 and 0.25. This is the current state of the filter. Okay, the filter implements 1 minus 0.5 Z inverse plus 0.25 Z inverse square. When I find that this error is non-zero, what do I do? If the error is positive, you have to reduce the value. So that actually, well, I mean, let's say we have ISI. You send a +1 pulse like this, and this is y hat. Okay, this is +1. Okay, and this is -1. So in this case, this is y. This is y hat. Y is less than y hat. But if it was the same negative pulse, this is y. This is y hat. Y is more than y hat. That doesn't work directly like that, right?
And accordingly, the error spectrum's frequency also we can go at tweak it. And then if we get a higher, lower frequency coefficient, we can go and tweak the first step.
You will detect the spectrum of the error. That itself is a difficult thing. How do you do that? Put a spectrum in analyzer inside the receiver. Huh? Okay. But okay, like will I increase the second tap and the third tap, or will I increase the second one, decrease the third one, or which direction do I go? So you will just move all of them in the same direction. So and what will you do next? I mean, it's supposed to be an algorithm. It's supposed to work even when you are not there. Once you set it up. How will you do that? Yeah, okay, that is fine. I mean, that is essentially what you want, right? You want to minimize the error energy or the mean square value. But how will you do that? Actually, that is something what you want to do, right? You have to look at the energy of the error or the mean square value of the error and minimize that. That's what you want to do. Okay. No. Firstly, the error value itself will vary continuously, right? Because that depends on the bit pattern. So if you have a long sequence of ones, it may have a small error. But if you have alternating ones, it may have a big error. So depending on the bit pattern, even if you don't do anything to the equalizer, the value of V will keep on varying. Okay, but what is in which direction will you? That's okay. You are now saying that you will adapt one tap and then adapt the next tap and so on. So that's okay. But how will you change it? Like in what direction will you change it? No, that's okay. Fine. But if the error is, okay, let's say if the error is positive, what are you going to do to the coefficient? Are you going to increase it or decrease it? What's that? Yeah. You will evaluate? Come again?
Sir, whatever tabs we are getting in the tab and the channel response.
Yeah, channel response you don't know. You only know the tab values, let's say. That's why you are doing the adaptation, right? You don't know the channel response exactly. So, can we or can we not? Okay. But like I said, it anyway, previous meaning from the previous time instant. So, like I was saying, if you keep the equalizer fixed, then just with the bit pattern, the error will keep on varying. Okay. Yeah. Okay. No, but how will you tweak it? Because see, if you, let's say you send a succession of ones, okay, the output, let's say, will look something like this. So you look at this sample, there is some error, you look at the next one, there is a smaller error. What are you going to do in this case? Okay. So, okay, one thing maybe trial and error, so you do one tap at a time, like you look at the value of E or let's say E square over a large number of bits, okay, keep the tap fixed, then you modify the tap a little bit, you look at that and try to do the kind of brute force least mean square. That is possible. Okay, let's see how to do it. It is possible to do it with, let's first take a very simple dummy case. It's not even an equalizer, okay. I just have a gain of C0. The input is a bunch of bits and I have the decision. I mean, this looks overly elaborate for what I am going to describe. There is only one coefficient. This is a first order FIR. Basically, there is no filter and there is no channel either. But I am just describing something here. How to. So what I want to do is this. The comparator will give me plus minus 1 decisions. I want to make sure that the output here, the sampled output here, also has a magnitude of 1, that is values of plus or minus 1. Okay, I want to get plus or minus 1 at this point. How would I go about doing it? So again, I want to do it using the difference between these two. And someone said the least mean square. So let's say I want to minimize the mean square value of E. How can I do that? What is E? Let's say this is X. I mean, let's actually operate entirely in the sample domain. So this is, these are samples which are plus minus 1 and I have a gain C0. So every signal here is in discrete time. So we don't have to add the sampler. So this is X of n, this is Y of n and I have the decision. After that I get Y hat of, and I take the difference between these two. Okay. and I get a sequence of error E of n, and I want to minimize the energy of E of n, and I know that if this has values of plus minus 1, then the gain of C0 is adjusted properly. This is actually not a filter yet, it's just an automatic gain control. I want to adjust the gain such that the amplitude here is 1. What is E? What's the expression for E in terms of C0x? And now to avoid confusion, I'll avoid clutter, I'll remove the time index, right? I'll just write E equal to C0x minus y hat. Okay, what is E square? Now I want to adjust C0 so that this function is minimum. How many minima does it have? 1 or more? It's a quadratic function, and this is minimum with respect to C0. Okay, it's a quadratic in C0, so it has 1 minimum. This is what it is. And if I plot the error with respect to, against C0, I get something like this. The location of this depends on x and y hat and so on. Okay, y hat is plus or minus 1, but it depends on x. But this is how it is. So this is E square versus C0. And where do I want to be? At the minimum. Actually, the minimum is at 0. The way I wrote it, it looks like the error is not 0. The minimum will be at 0 for this particular case. So let's say I'm here. Okay. So when I start off, the value of C0 is here. I need to introduce another index because and now the coefficient is also time varying. As I do the adaptation, the coefficient varies with time. So initially the value of C0 is here. So how will you choose which direction to move in? You will compare E of n with E minimum, and so if you do that, so here E square is positive and here it is negative, also positive. So here you have to move, here you have to decrease the coefficient, here you have to increase the coefficient. Slope. Yeah, you need to look at the slope, right? You need to look at the slope of this. And do what? Yeah, you just change it in the direction of the slope. You need to look at where the gradient is and change it, right? Change the coefficient. So this is how you do the minimization. Okay, so you start with C0 here, and then you know the direction of the gradient is like this. So what do you do if so this index k refers to the time index of the coefficient. I have the coefficient at k minus 1, I want to update it to the coefficient at k. So what do I do with the slope? And I have the slope also. Okay. So this should be plus or minus? Minus? Plus or minus? Minus. So clearly, from this it's very obvious. If the slope of E square versus C0 is positive, I have to reduce the coefficient, and if it is negative, I have to increase the coefficient. And I'll have a scaling factor here. Just for definition, I'll call that scaling factor mu by 2. Okay. Why do I need the scaling factor? Is there any significance of that? Yeah, so what I don't want is, here I know that I want to decrease the value of C0, but I don't want to decrease it so much that I go here. Then again, if I use a very large step, from here I will go back there or something, it can even diverge. But if I choose a very small step, and again, how small is small, I have not defined so far, but if I use a small enough step, you can see that maybe from this point you come to the next point where the error reduces, and then it reduces further and so on. And finally, this is a kind of digital control system, so it will keep bouncing around between some small values of error. Okay, that's what it will do. Is this okay? At least you get the idea here. So this mu by 2 is the scaling factor. And what is this? What is the derivative of E square? How do we find that? Huh? Difference between what and what? No, this is not derivative with respect to time. This is derivative with respect to coefficient. Actually, yeah, I should have pointed that out earlier. When you deal with this LMS and all these things, you get a lot of derivatives. The derivative is not with respect to time. It is with respect to the coefficient. How the error changes with respect to the coefficient. With respect to time, it will keep on changing simply because the bit pattern is changing. That's not of interest. Okay? you want to make it small for all time, roughly speaking. Or when you say mean square error, you have to minimize the average of the error square. So this is the derivative with respect to the coefficient. What is that value for this particular system? Input and the error actually. So this is d by dc naught e square is 2 times e d by dc naught, and what is this? d by dc naught x, 2 times e times x. So that shows mu by 2 so that this 2 cancels out. Is this okay? So in this particular case, the squared error was a quadratic function of the coefficient, right? Then, so it has a single global minimum, there is no other minima, there is only one minimum. Then you look at the gradient, and based on that you can choose to increase or decrease the coefficient. And the value of the gradient with respect to the coefficient is nothing but the error times the input. No, firstly error is both positive and negative. So when you say minimize, it will go to minus infinity. Right? Absolute value. Yeah, I think it's harder to get an analytical expression in that case, that's all. But if you minimize e square, you are minimizing the absolute value also. And of course, the minimum mean square error gives you the best performance in presence of noise. We have not dealt with that here. Here there is no noise, but that's an aside. So are you convinced that this thing works? Finally, the value of C0 will converge to a point where the error is 0. So this is a way of doing automatic gain control. There may be other ways of doing it, but this is just automatic gain control as it stands now. So this is of some use, but what I started off was with the filter. So what do I do in case of a filter? Huh? No, there will be multiple weights, right? There is C0, C1, C2, C3 and so on. What do I do with all of them? Okay, then will it be like this or will it turn out to be something else? Okay. Different sums. So what he is saying is the same expression holds for every coefficient. Like I wrote C0 of k is this, then I can write C1 of k is the same thing, C1 of k minus 1 minus this. But what is x? Pass so many inputs.
If we want two coefficients, we take the current input and the path. Path answer.
Okay.
And then instead of having d by dc naught, we have double dc.
Okay, that's fine.
Maybe a convolution of the error, the current error and past error, and the current sample and the path.
So, but you need to get a single number here, isn't it?
Yeah, sorry. Dot.
Okay. Huh? We don't have access to? No, in this case, I am just adjusting the gain, so I do have access to this. Yeah, let's see what we need to do. So this is, the fact that it's a filter is incidental. What we are concerned with is a case where we have a linear combination of some n quantities. Okay. Maybe I'll make this x0 to xn minus 1. And now we have to tweak the values of C0, C1, Cn minus 1 so that the error between the decision and the input to the decision block is minimized. That is, the squared error is minimized. Anyway, you can evaluate the expressions by doing exactly the same thing and see what you get. I think we have to stop at this point.